Welcome to Maths with EJD. In this video, I'll be talking about the reaction diffusion equation, still under partial differential equations. So let's have an overview of that. So reaction diffusion equations describe how substances spread. In fact, it should be react before spread, right? How substances react and spread. So you have a reaction and then you have a spread. With applications in chemistry and biology. So reaction, then diffusion, including, so you have this in pattern formation and wound healing. Because all this happen in space and time, they are best described using partial differential equations. So reaction diffusion equations take the form, partial U, partial T equals D grad squared U plus R of U. So that's the form they take where U is the concentration, as the concentration of whatever you are reacting or like that. Then D is the diffusion coefficient. So it determines how fast something spreads. So D is the diffusion coefficient. Then you have del squared U, which governs diffusion. So this governs diffusion. Then you have R of U. R of U represents reactions. Represents the reactions taking place. Okay. Now, steady states occur. Steady states occur when partial U, partial T is equal to 0. And that implies, so implying that D grad squared U plus R of U equals 0. Okay. Now let's take some applications now. So let's take applications in chemistry. So, okay, I'll take one application in chemistry. So, and that will be our first example, example 1. So we talk about the Belousov-Zhabotinsky reaction. Belousov-Zhabotinsky reaction, which talks about chemical oscillations. Chemical oscillations. So that's what the Belousov-Zhabotinsky's reaction is about. So here you have models. It models oscillating waves. It models oscillating waves with activator U. You have an activator U and inhibitor V. So as a result of that, you have a system of partial differential equations, partial U, partial T equals du. This would be like the activation coefficient, if you like, del squared U plus U minus U cubed minus V. And then you have partial V, partial T, and then you have dV. That would be like the inhibition coefficient, and you have del squared V, del squared V plus epsilon into U minus V, like that. So let's look at an example. What example? Let me just call it. Okay, well, let's just go on. So imagine a setup for this. So we can have this setup. Say du is equal to 1. That's the diffusion, the inhibition activation coefficient. And then you have dV, which is the inhibition coefficient, which is 0.1. So it means that the rate of inhibition is slower than the rate of activation. Okay. So maybe something spreads three times and then it is stopped once, something like that. Then let's take epsilon. We have epsilon to be 0.01. Okay. And then we have a 2D grid since we have UV. So we can have a two-dimensional grid, which is 100 by 100. That's if you want to implement it numerically. So that really helps. I guess I want to make that come out better. So we have a two-dimensional grid, which is 100 by 100. So that's like the setup we want to use there. Then next, we have the initial conditions. Initial conditions. So we can have random perturbations. Random perturbations around the origin. U equals 0 and V is also equal to 0. Then after that, let's talk about the solution itself. For the solution, so solution, you can use finite differences, which I've done before under numerical analysis. I'm going to put those videos at the end of this playlist, talking about numerical solutions. Finite differences, we can use Euler method. You can use the Euler method with delta T equals 0.01. Okay. Then you'll see that after 1,000 steps, spiral waves form. Spiral waves get to form. Okay. Then talking about the steady state now. Steady state. So for the steady state, as usual, we set delta U, partial U, partial T to be equal to partial V, partial T equals 0. In the same way, grad squared U will be equal to grad squared V. That is equal to 0. And this talks about uniform states. So you have a uniform state now. So any derivative there just goes to 0 for uniform state. Uniform state. Okay. So in that case, if we solve now, so want to try to solve, and we have, so looking at the original setup, right? You see, this will go to 0, all this will go to 0, and this is what we have left. Okay. So we can take care of that. So we want to solve U minus U cube minus V equals 0. And then we want to solve that together with epsilon into U minus V equals 0. Okay. So, I mean, so if this is the system we're trying to solve, right? Let's call this 1 and call this 2. So you can already see that from 2, where epsilon is you have epsilon to U minus V equals 0. So that means that epsilon is equal to, it is important that epsilon is not equal to 0, right? If epsilon is 0, we have nothing to work around. So in that case, we can divide through by epsilon. We have U minus V equals 0. And that implies that U is equal to V. And with U equals V, things are simple. we can progress with that. And then we can then have, so we can say from one, right? From one, we now have u minus u cube minus u equals 0. Or better still, that's like, I mean, that's basically, this cancels this now. So minus u cube is equal to 0. So that tells us that implies that u is equal to 0. So at the end of the day, at the steady state, u equals v equals 0, basically. And okay, so thus u comma v is equal to 0 comma 0. Okay, now linear stability analysis, that's the normal Jacobian stuff that we do. Linear stability analysis shows this state is unstable. So if we try this 0, 0 thing, it shows that it is unstable because the eigenvalue, so eigenvalue would be lambda, which lambda is equal to 1, and that's greater than 0. And any lambda greater than 0 shows that the system is not steady. So lambda is equal to 1 is less than, I mean, lambda equals 1 is greater than 0, right? For d du into u minus u cube minus v, which is equal to 1 minus 3u squared. And that drives oscillation. So driving oscillation. Okay. And finally, still talking about this chemical, Belousov-Zhabotinsky reaction as an example of reaction-diffusion equation in chemistry. So the significance of this will be this significance. The unstable steady state leads to sustained waves mimicking, because of the sustained waves, it mimics the Belousov-Zhabotinsky, that's like complicated name, Zhabotinsky, yeah, Belousov-Zhabotinsky reaction dynamics. Okay, so that's one nice example in chemistry. At this point, let's switch over to this now, and then it can go with green. Let's do that. So here, so let's talk about applications in biology. Applications in biology. So applications in biology. So that takes us to example 2, following the BZ reaction. Example 2. So this example 2 will consider Turing patterns in morphogenesis. Turing patterns in morphogenesis. So Alan Turing, a computer scientist, was able to, I mean, it's one of his last interventions in science was about pattern formation. So Turing patterns in morphogenesis. Okay, so this idea actually explains biological patterns, with activator. So we have activator U and inhibitor V. So basically the same like before, right? Except that here we're talking about pattern formation in maybe animals or plants. So the equation is something like this: partial U partial T equals du grad squared U plus A minus U plus U squared V. And then we have partial V partial T equals dV grad squared V plus B minus U squared V, like that. So if you want to look at the setup, it's more like this. Set up. So imagine that du is 0.1, dv is 10. That means uh the inhibition is 10 times of the activation. Okay. So inhibition is faster than activation. So with that, then we now have A to be 0.1, B is 0.9, and we can do that in a one-dimensional domain. Okay, not grid now. So where X belongs to the closed interval 0 to 100, okay, in the one-dimensional domain. Then we can talk about the initial conditions. So if you want to write a code, these are guidelines that you can follow. I'm going to show a Python code definitely at the end of the day, just one example at least. So here, so you have noise around would be something like U is 0.1 and V is 0.9. Okay, then we talk about the solution itself. How do we solve that? Solution. So finite difference is useful here. Finite differences with delta t equals 0.05 in 5,000 steps. 5,000 steps. Okay. So in that case now, uh, so this in 5,000 steps. So we see that stripes form along the line with a wavelength uh, that is approximately square root of dv over du. All right. So stripes form, right? And the wavelength is approximately square root of dv over du. Okay. So then we have the steady state. So for the steady state, of course, we know that happens when we set du dt equals dv dt equals 0. And we also have grad squared u equals grad squared v. Anything involving derivative just goes to 0. And then we now solve. So we solve a minus u plus u squared v equals 0. And we solve b minus u squared v equals 0. So these two, so this is equation 1, this is equation 2. Of course, from the look of things, we can just add up and then these two will cancel out. Okay, so we have adding 1 to 2, because since one is positive and the other is negative, so we have a plus b minus u, and those other this cancel out, and that is equal to 0. So we can easily get u. So we see that u is equal to a plus b very easily. U is a plus b. So since u is a plus b, interestingly, we have values for a and b. So that means u is equal to a is 0.1, b is 0.9. So that implies that u is equal to 1.0, or just 1 if you like. So we have that. Then what do we do next? So since we have that, we have u now, then we can go for v. So we can take any of the equations. So we can say, let's say from equation 2. So from equation 2, we have b minus u squared v equals 0. Okay, so we can get v from here. Although we already know we can get v, right? So b is equal to u squared v. So v is b over u squared. That means b all over a plus b all squared. Okay, so but we know b is 0.9. A plus b is 0.1 plus 0.9 all squared. That's 0.9 all over 1 squared. And that is simply 0.9. So we have v to be 0.9. Keep that. So the steady state is such that you have u comma v equals u is 0.1 U is 1.0. So you have 1.0, comma 0.9. That's a steady state. What else do we do? So we have Turing instability. So Turing instability. So that leads to faster diffusion. Faster diffusion. Of course, U is diffusion and V is inhibition. So, and 1.0 is greater than 0.9. So we have faster diffusion of the activator. All right. And that destabilizes this. So Turing instability destabilizes this, forming patterns. So it forms patterns like that. So what's the significance of this story? The significance, this explains zebra stripes. This explains zebra stripes via instability, of uniform state. Okay. So then let's move on to another interesting example. So I can use this and come here and use this. All right. So example 3, still under biology. Example 1 was under chemistry. Example 2 and 3 are, I guess 2, 3, and 4 even are under biology. So example 3. So here we want to talk about the Gray-Scott model. Gray-Scott model, which still talks about pattern formation. Pattern formation. So the other one was talking about morphogenesis, right? So this Gray-Scott model actually simulates diverse patterns. So if you look at patterns in leaves and animals, so some of these things can explain them. So you have partial U, partial T equals du grad squared U minus UV squared plus F into 1 minus U. That's one equation. That's the activator. And the inhibitor, as usual, is dV dt. So so dV dt is dV grad squared V plus UV squared minus F plus KV, like that. So so you can then imagine a setup like this, that du is 0.2, dv is 0.1. Then the F you see up there, the F is 0.055, K. Then K is 0.062. Then we have a two-dimensional grid. Which is 200 by 200. Okay. So again, we talk about initial conditions. So here we take U to be 1 and V is equal to 0, except U is 0.5, or better still. So U is 1 and V is 0, except U is 0.5 and V is 0.25 in a square. Okay. So the solution here, to get the solution, you can use finite differences with delta t equals 1 in 10,000 steps. 10,000 steps. So this actually replicates Sport's form. Okay, I'm going to show a Python code on this particular one as an example of all the others. So let's look at the steady state. Of course, we already have anything that involves derivative goes to 0 for steady state. So set up, or rather set partial u partial t equals partial v partial t equals 0, and grad squared u equals grad squared v, and that is equal to 0. And then you can solve minus uv squared. Of course, everything involving derivative is gone to 0. So this will go, this will go. I will just have this and this now because all this will also go. Okay, so we want to solve minus uv squared plus f into 1 minus u equals 0. And then the other one is uv squared minus f plus kv. So you have, again, uv squared minus f minus, that's uv squared, right, into f plus kv equals 0. So this is what we want to solve. Now this is equation 1, if you like, and this is equation 2. So again, it's easy. We can just add, and then the UVs will go. Is that the best strategy to use here? I think so. Or okay. Trying to see the best way to handle this. Okay, from second equation, we can factor V, right? And if we factor V, good, that works. So from 2, we have UV squared. We have UV squared. And then minus F plus KV equals 0. So we can factorize V. So we have V into UV minus F plus K equals 0. So the V here is outside. So here we see already that V is equal to 0, or UV minus F plus K is equal to 0. Okay, so that means that V is 0, or UV is F plus K, like that. So we can now have two cases. Let me use a lighter green. This. So you can have two cases. So like you can have case 1 where V is equal to 0. So you can use that in the first equation. So in this case now, from equation 1, where you have uv squared minus f of f plus k v equals 0. No, uv squared plus f into 1 minus u equals 0. So minus uv squared, okay, minus uv squared plus f into 1 minus u equals 0. But we have v to be 0, so that means we have minus u into 0 squared plus f into 1 minus u equals 0. So this goes, and we just have f minus f u equals 0. So that means that we can easily get our u here. So we have f equals fu. Divide both sides by f. We have u to be equal to 1. I mean, that means we have f over f equals fu over f. This cancels. So u is equal to 1. So in that case, we have a steady state. So the steady state here would be u comma v equals 1 for u and 0 for v. Okay, that's one case. Another case would be for case 2 now, the case where uv is equal to f plus k. So we can put that in the first equation again. So we have minus v squared, again from the same equation 1. From equation 1, we have minus uv squared plus f into 1 minus u equals 0. So if we put u, and we see we put uv for f plus k, that means that we have minus u, then v is f plus k. All right. Yeah, f of k all over u all squared plus f into 1 minus u equals 0. So we have minus u times f plus k all squared all over u squared. So this u cancels 1u plus f into 1 minus u equals 0. Okay. So we now have yeah, we can multiply through by u, right? So we multiply through by u. So we have f plus k squared plus f into u, f u into 1 minus u equals 0. Okay. So from here, we can have a quadratic expression in terms of u. So that is f plus k squared plus fu minus fu squared equals 0. So that's minus fu squared plus fu plus f of f plus k all squared. Okay, this is actually minus here, so if you don't lose sight of that. So this is minus, all of this is 0. So multiply through by positive, so we have, or in fact we can actually multiply through by, yeah, let's multiply through by minus first. So we have fu squared minus fu plus f plus k all squared equals 0. So that if you divide through by f, so you have u squared minus u plus f plus k squared all over f equals 0. So we can find u like this. But since we already have values for f and k, so you remember we had values for f and k given up here. So we have f to be 0.00055 and k 0.062. Okay. That means we have what do we do? Trying to see. Okay, let me take it all the way. So since f is equal to 0.055 and k is 0.062, so we have u squared minus u plus 0.055 plus 0.062 divided by 0.055 equals 0. So that u squared minus u plus we punch the numbers and get it. Oh yeah, this is squared, by the way. This is squared. So I'll just do everything and get the result at once. So I have 0, 0.055 plus 0. Is it 0.062? I think it's 0.062, yeah? 0.062, 0.062 raised to power 2 divided by 0.055, 0.055. So that gives us 0.24, 0.2489 equals 0. So we can get u. U is simply minus b plus or minus square root of 4ac, b squared, right? B squared minus 4ac all over 2a. Okay, so that means, of course, a is 1, the coefficient of u squared, b is minus 1, the coefficient of u, and c is the constant 0.2489 that we got here, 0.2489. So u is equal to minus 1 plus or minus square root of minus 1 squared, then minus 4. A is 1, C is 0.2489 all over 2 times 1. So we have u to be 1 plus or minus square root of 1 minus 4 times 0.2489. So that is 4 times 0.2489. That is 0.9956. Okay, all over 2. So u is 1 plus or minus. So now 1 minus 0.9956 is equal to square root of 0.0044 all over 2. So u is equal to 1 plus or minus. So square root of that, right? So square roots of 0.0044. That's okay, square roots. Okay, square root. Yeah. So that is 0.0663. 0.0663 to 4 decimal places divided by 2. So that means that U1 will be, let's say, the positive one. So that was just be 0.0663, and U2 would be the negative one now. That's 1 minus 0.0663. So that is 0.9337. 0.9337. Okay, so these are the values of our U. So we have two values of U in short. So with these two values of U, what do we do? So we have U1, U2 to be all this. Okay. Reaction diffusion. So we have these two values of U. So it means that what value did you already have V before we got here? I guess no. I guess I just want to, maybe I should leave this hanging here so it doesn't take further more time. Okay, so for the gray Scott model, the system evolves in replicating spots. Okay. Yep. Or did I jump something? Let me see. Turing pattern in for morphogenesis. Then we have this now. Okay, yeah, we're still here. Steady state. Okay, that's towards the end. Yeah, steady state. Yeah, we're here. So I've got the values of U1 and U2 now. So um and so given this F plus K, yeah, because we have UV to be F plus K from here, so it's either V is equal to 0 or UV is F plus K. So I can still go further. So I say from UV equals F plus K. So I can have U1 V equals F plus K. So U1 is in short, what we need here is V, right? So V is equal to F plus K all over U1, and F plus K is F is 0.055, then K is 0.062 all over U1 is now 1.0663. Okay, so in this case, V would be, so of course we are automatically, yeah, V in this case would just be that expression. I never saw this intensive thing come, it's okay. 0.055 0.055 plus 0.062 0.062 divided by 1.0663. Right? That gives us V to be 0.1097. So all of that, so the whole thing there implies that U comma V is equal to U comma V is equal to, what's the U here again? Oh yeah, 1.0663, comma 0.1097. That's that. And we can also do the other one where we have U2V equals F plus K. So meaning that V is F plus K all over V2. That is 0.055 plus 0.062 all over V2 now, which is 0. V2 0.9337. So 0.9337. So that means V, oh, this is U2, sorry. So V is equal to V is equal to 0. Okay, that now just divide by 0.9337. 0.9337, and that is 0.1253. So again, we have, so the whole thing implies that UV here is equal to the U to that 0.9337, comma 0.1253. Okay, so that's at the steady states. We have the two different steady states in that second situation. Okay, so with that in place now, okay, so if we have the first one, which we already have, right? In the first case, we just had 1 comma 0. Okay, so I'll just make a comment about that and move on to the next thing. So the steady state 1 comma 0 is often stable, but perturbations with chosen parameters drive spots. They actually drive spots. So we are going to see an example of this. So what is the significance of the Gray Scott model, which is a pattern formation model? The significance of that tells us that patterns arise. Patterns arise from instability of 1 comma 0. So if 1 comma 0 is unstable, so in that case, that will modeling cell growth. So that models cell growth. Okay. All right. Let's move on to, okay, I guess I'm still on with this. Okay, let this come here now. And I have, let me use black alongside. Okay, would this be the last example? Yeah, I think so. Last example, I guess I won't waste too much time on the steady state this time around. So let's talk about example 4. So 3 examples under biology now. Example 4, that is wound healing. So we can model the healing of wound using partial differential equations, since that happens in space and time. So we have cell migration. So that deals with wound healing, deals with cell migration and chemical signaling. Okay. So this actually models cell density n, and growth factor C. Okay. So that you have dn dt equals dn grad squared n plus Rn into 1 minus n over k. Now, there's also a carrying capacity here because there's a limited cell area the cell can, any healing cell that is healing a wound would cover. So So you have the C dt also. The C dt is the C grad squared C plus alpha n minus BC, okay, beta C that is. So, and the setup would be something like this. So imagine the setup, dn is 0.01. Okay, that's the cell density. So the cell density is 0.01 and the growth factor is 1. So the growth factor is bigger than the cell density that is. So R is 0.5, K is 1, delta is 0.1, and we do that in a 2D domain, 50 by 50. So the initial conditions. So the initial conditions for the wound. So we have wound, cell density is 0, growth rate is 0. That's the initial condition. In the tissue, then N is now equal to 1 and growth rate is 0.2 or growth factor is 0.2. Then we talk about the solution. How do we solve this? Solution, you can use finite differences. You see, finite difference is powerful. So we can use finite differences with time step 0.1 in 2000 steps. So we see that wound closes when cell density is approximately 1. Okay, so like the wound gets healed. Of course, for steady state, we know how that goes. I won't take too much time on that. Steady state. So for steady state, you can take this as a task. So set partial n partial t to be partial c partial t to be equal to 0, and grad squared n equals grad squared c, and that is also equal to 0. So what we basically want to solve will be this system, Rn, because everything involving derivative is gone, like all these ones are all gone. So you're just left to solve all these things without derivatives. Okay, so you just basically need to solve Rn into 1 minus n over carrying capacity minus delta nc equals 0. Then you have alpha n minus beta c equals 0. So I want to solve this as a system of equations for n and c. So you're solving for n and c. So you need n comma c, basically. That's what we need from all that. So I'll just refer to some possibilities. Okay, so you're going to have, you can have steady state, can have the steady state, which is n comma c equals 0, 0, when this cell density is 0 and the growth factor is also 0. That's one situation. Then you can have another case where n comma c, okay, this just tells us that there's no tissue, no tissue. That's what this means, no tissue at that point in time. Then NC, so for NC, which is approximately 0.714 and 1.434. So 0.714 for N and 1.43 for C. So this actually tells us that some healing is taking place. So this talks about healed tissue, healed tissue with active signaling, healed tissue with active signaling. So, and then stability depends, on parameters. So the kind of parameters they use will determine how the stability looks like. Here, 0.714 and 1.43 actually attracts solutions post healing. And what is the significance of this whole thing? Significance. So it models skin repair with steady state, reflecting healed tissue. Okay, with all this done, so let's talk about some key insights. Okay, I mean, I'll just say it verbally. In chemistry, right, we have the BZ on stable steady states. Okay, I want to write key insights from all the examples we've seen, right? Um, so for the chemistry examples, right? Chemistry, Belousov-Zhabotinsky or something. BZ's unstable steady states, unstable steady states, 0, 0 drives oscillations. Drives oscillations. Then we have biology. So for biology, Turing, and Gray Scott, patterns emerge from destabilized uniform states. So we see that wound healing evolves toward a healed state with cell density 0.714 and growth rate 1.43. Okay, then we'll talk about steady states. So steady states we have uniform states often exist but are unstable, like all the 0, 0s we saw. So that instability, so it guides processes like healing or pattern formation. So these examples highlight reaction diffusion's role in pattern formation and dynamics with steady state shaping outcomes. Okay. So yeah, before I forget, I have a Python code for Gray-Scott model. Give 4 examples. I think the fourth one is it's wound healing. Okay. The one I have a Python code for is, I think, example 3, where we have the Gray-Scott model for pattern formation. Yeah, so let's check that out. Okay, so yeah, so this is it right here. So Gray-Scott reaction diffusion model. So we have the diffusion coefficient for the activator U and the diffusion coefficient for the activator V. And then we have all the feed rates F, the removal rate K, right? Then LX, LY, the grid system 200 by 200. DX, that's one time step. I mean, DX spatial step, right? And time step is one. We take total time steps to be 10,000. And, I mean, you can study the whole of the rest of that. The center is this LX over 4 and the rest of them. So you can check that out. You see it on either Facebook or YouTube. On Facebook, because I can't put it on YouTube. So this takes a bit of time because it's a lot of work. So you see at time 1000, see what the pattern is like. Looks like a rectangle with some pulled up shape. At 2000, you see the pattern is formed better. At 3000, things are getting a bit more complicated. So when you see patterns like this in leaves, you can already imagine what's driving it. At time 4000, 5000 is more complicated, 6000 same. And then it's still on, it's not done yet. Yeah. So at time step 7000, you still have V to be this. So by the way, okay, it's been V all the way, right? By the time it's all done, we now have V and U side by side when the process is complete. So at time 9000, see what you have. Then at time 10,000, it's too complicated. So we have final U and final V. So it's more like U plus V gives us the universal set. So if you remove V, you have U because they are working together. So as U is trying to spread, V is trying to stop its spread. So it's more like all those blockages is what makes the patterns to not move in a particular direction. So you have that activator inhibitor thing going on, and then you have pattern formation like this. So this is really interesting. So reaction diffusion is quite an interesting thing when it comes to talking about partial differential equations. So I'll just stop here. So this is the end of the video. Let me know in the comment section how helpful these videos are for you, and if there's a topic you'd like me to teach or a problem you'd like me to solve. If you have not subscribed to the channel, please go ahead and do that. If you have, thank you. And don't forget to subscribe to hit the notification bell so you can always get alerted each time a new video is released. Uh, be sure again to like and share so that more people can have access to the great content we have here. Till I come your way again, keep doing math right. Bye.